Okay, so this is a video that covers the first part of structure and bonding topic, GCSE topic in the combined science GCSE. And I just want to open by showing you or pointing out the front cover for the specification. And I think it's really important that whenever as you're working through any of your GCSEs, but obviously I'm going to focus on the chemistry part of science, that you are regularly or often or occasionally even referring to what the actual specification says. So when we go through this video, as we talk about the different parts and look at the different things, I will be showing sections from this specification. Now the reason for doing so is because this sort of sets out or lays out what the exam board, AQA, requires of you and what they can test you on. Now there's always a little bit of a, they don't itemize every single thing, but they make it clear, I guess, what you need to make sure that you're aware of going into the exam. And really, they can't ask you anything beyond that. So anyway, we'll look at the different sections as we go through, and hopefully they'll make sense. But that's essentially what we're going to be covering. We're only covering what the specification asks us to cover. So the first part of the specification for the sort of structure and bonding topic says chemical bonds. And I'm not going to read this out. You can pause the video and read what it says. But what I am going to do is I'm going to highlight, or I'm going to take, as we work through the next few bits, I'm going to take out sort of key points and sort of treat them as learning objectives. And so when you see the learning objectives that come up, they are essentially taken from this text, which is what the specification is telling you need to know. So here are our first two learning objectives. So firstly, it says state the three types of strong chemical bonds. So really this is just introducing to us the idea that there are, we can describe three types of chemical bonding. I don't personally like the word bonds. When we look at the three types, for me, we can only use the word bonds for one of them, and really I would prefer to use bonding for the others. And my reason, which I'll repeat or make clearer as we go through, is that I think bonds makes you think of single connections or singular connections, and in two of them there isn't really such a thing. And then the next thing that they're asking us to do, or the next learning objective, it says for each bond or for each type of bonding, state what it is, where it occurs, and the particles involved. So we might not cover every single part of that statement immediately, but we'll certainly cover the important parts, and we will certainly cover the other parts in the next few minutes. Now, for you to be able to do any aspect or any part of this topic, to be able to identify which of the three types of chemical bondings that we're going to look at are present in a particular substance, you need to be aware, you must know where the metals and the non-metals are on the periodic table. And really it's a no-go if you can't do that. I mean, it's chemistry is a very joined up subject, and it really does build upon itself. And one of the key foundations for this topic is knowing exactly where the metals and non-metals are. So I'm sure you've been taught this. I'm sure you've seen it, and the idea of a sort of a staircase, and it's about remembering where it starts, and it starts between aluminium and boron. And so aluminium, if you think about drinks cans and cooking utensils, that is clearly a metal. You may not know about boron, but if you just remember that aluminium is in effect where we're starting from, and then we go down in a series of steps. We don't need to go any further. And then to the right of those steps are the non-metals. And to the left of those steps are the metals. And the one that we just have to be also aware of is hydrogen, and hydrogen is a non-metal as well. So everything to the right of the steps, so here, they're all non-metals, and then we've got to include hydrogen as well. and then everything else, so the majority of the periodic table, maybe 2/3 or more, all of this here, these are metals. And when we start looking at compounds or substances, so not just compounds actually, sorry, but substances, chemical substances, knowing the elements that make those substances up, knowing whether they're non-metals or metals, is going to be absolutely fundamental. So here are the three types of bonding, right? So the first sort of learning objective is state the three types. Well, now we're just simply stating them. Stating them just says almost like listing them. So we've got ionic bonding, covalent bonding, and metallic bonding. And we can tell whether a substance or which of those bondings a substance has through a combination of the elements. So for ionic bonding, our substance has to be made of a metal and a non-metal. Could be more than one non-metal, but there must be a metal and a non-metal present for it to have ionic bonding. For covalent bonding, we're going to write non-metals only. And then for metallic bonding, it's going to be metals only. So it's like a classification system, right? So if you look at a substance and you know from its name or its formula, you can see from that it's got a metal and a non-metal, or even more than one non-metal. But as long as the combination of those two types of elements, well, then we're definitely going to have ionic bonding. If we look at a substance and we can only see a non-metal or non-metals, then that's going to have covalent bonding. And if we look at a substance that has only a metal or metals in it, then that's going to be metallic bonding. So it's a simple classification system. And we're going to be building on this shortly, and we're going to be learning a lot more about each of those types of bonding. Before we do that, let's just test what we've just said. So let's just have a look, list at a variety of compounds and decide which type of bonding, based on what we said, is present in each. So I suggest you pause the video, get a piece of paper, and write what bonding you think is present in each of these different substances, and then we'll take a look at the answers. Okay, so the first one, lithium fluoride. So lithium is a metal, fluorine is a non-metal, so we have a metal and a non-metal, so that must be ionic bonding, or must have ionic bonding, sorry. The next one, calcium oxide. Calcium is a metal, oxygen is a non-metal, so that is also going to be ionic bonding. Then the next compound, which is silane, not that you were expected to know that or even remember it, but SiH4. So if we look at our periodic table, silicon is a non-metal, hydrogen is a non-metal, so we have non-metals only, so we have covalent bonding. Next we've got hydrogen sulfide. Hydrogen is a non-metal, we need to remember that because it is a little bit isolated on the periodic table. Sulfur is also a non-metal, so that is covalent bonding. H2O, hydrogen, we've already said is a non-metal. Oxygen, we've already said is a non-metal, so that also has covalent bonding. Then we've got just aluminium. So aluminium is a metal. We don't have anything else, so it's metals only. So this has metallic bonding. And then we look at iron straight afterwards. That's also on its own. It's the only element, and that is a metal, and so that must also have metallic bonding because it's a metal only. Then we have ammonia. So NH3 is the formula for ammonia. So we have nitrogen, which is a non-metal, hydrogen, which is a non-metal. So we have covalent bonding. Then we've got phosphorus bromide, or phosphorus tribromide. So phosphorus is a non-metal, bromine is a non-metal, so that has covalent bonding. Then nitrogen dioxide, Nitrogen is a non-metal, oxygen is a non-metal, so we again have covalent bonding. Then chlorine. So chlorine is a non-metal. There may be two chlorine atoms, but they're obviously the same atom, so that's non-metals only, so that is also covalent bonding. Fluorine, just like chlorine, two atoms, both are the same, but they're non-metals only, so that has covalent bonding. Then we have magnesium fluoride. Magnesium is a metal, fluorine is a non-metal, so we have ionic bonding. Then just zinc on its own. Zinc is a metal, metals only, so metallic bonding. And then finally we have hydrogen. Hydrogen is a non-metal, so we have non-metals only, so we have covalent bonding. So our second learning objective was for each bond, state what it is, where it occurs, and the particles involved. So this doesn't quite answer exactly that objective, but what we want to understand is what is common to all of them. So we are talking about chemical bonding, and then we've said there are now we can classify it in three ways. We can say ionic bonding, covalent bonding, or metallic bonding. But what does it mean to even say chemical bonding at all? So fundamental to all chemical bonding is that there is, we're going to unpick this each bit by bit, but there are forces of attraction, and they're always between oppositely charged particles. So by oppositely charged particles, we mean negative and positively charged. And if you have negatively and positively charged particles, and if there is an attraction, then that is an electrostatic force of attraction. So the electrostatic is referring to positive and negative. And then what is a feature of all of these three types of bonding is that attraction that forms is very strong, or is strong, I should say. So strong is going to be a key word quite often when we're talking about these types of bonding and the properties that result from them. Electrostatic is because it's always about between oppositely charged particles. Force of attraction, because that's what you get when you have positive and negative particles close by, they attract each other. And what's going to differ between or what's different, I should say, between ionic bonding, covalent bonding, metallic bonding, they all have these electrostatic forces of attraction between oppositely charged particles, but what's going to differ is what those charged particles are, right? So this will become clearer, but there will always be opposite charges. There will always be a strong electrostatic force of attraction. But what those oppositely charged particles are is going to differ in the three types of bonding. Now, why does bonding happen at all? So the consequence or result of all bonding, whether it's ionic, whether it's covalent, whether it's metallic, the consequence is that the atoms involved, or the elements involved, will achieve full outer shells. Now, they may no longer be atoms, as we'll see, but those elements will have achieved full outer shells. Because if you think about what you did in atomic structure, and you think about your periodic table, and you think about your groups, what you know is that in your atomic structure, your first shell could hold 2 electrons, a maximum of 2, and then your second shell and third shell could hold a maximum of 8. And then, that was when they were full. So when the first shell had 2, it was full. When the second shell had 8, it was full. When the third shell had 8, it was full. And the group numbers, one of the other things you learned was that the group numbers on the periodic table told you how many electrons were on the outer shell for that particular element. So if we think of the second period and the third period, groups 1 to 7 all have incomplete outer shells, because none of those elements in those groups have 8 electrons in their outer shell. So the the result of all of the bonding we're going to discuss is going to be about achieving full outer shells, and that is something I'm going to stress as we go through each of them individually. Now, how they're going to achieve full outer shells is going to depend on, it's going to depend on a variety of things, but essentially they're going to achieve that full outer shell by either losing electrons, gaining electrons, or sharing electrons. So one of these three things is going to happen to each atom of each element involved in bonding. So they're going to always get a full outer shell if they're bonding, or always achieve a full outer shell if they're bonding, and they're going to do so either by losing, gaining, or sharing electrons. So there's a repeat of that first part of the specification. There are little details in here that we haven't yet actually covered, because I think really it makes sense to do that when we come to those or come to them individually. So, for example, we haven't yet said that in ionic bonding, it's about that we've got oppositely charged ions. We haven't yet said that in covalent bonding, we're talking about shared pairs of electrons. And the other thing that we haven't said is in metallic bonding, the particles are atoms, which is actually wrong anyway. And shared delocalized electrons. I don't really like that. That's a part. So even though I'm highlighting it, I actually don't like that as a description. The other thing that hasn't really been mentioned is this word here, alloys. So that'll be something that we come across later. But essentially, an alloy is a mixture of which mostly it's a mixture of metals, but you can have, in the case of something like steel, it can be a mixture where it's mostly a metal, iron, but it can have a non-metal as part of that mixture, carbon. But anyway, we'll deal with that when we come to it properly. But otherwise, we've pretty much covered what it says there in terms of what the specification says. So now we're going to look at ionic bonding more closely. So we've stated the three types of bonding, and now we're going to look at them individually. We're going to look at this idea of losing, gaining, or sharing electrons, what's relevant where. So we're going to look at them at three in turn. We're going to look at ionic bonding, then covalent bonding, and then metallic bonding. And that'll basically bring us to the end of this section, or the end of this video. And then a subsequent video will look at, well, what are the consequences of those bonding? Like, what properties do the compounds have that have those particular types of bonding? So, but for the moment, we're just focusing on the bonding as bonding. So there are our learning objectives again. So the first one, we can see it's about how ionic bonding comes about in terms of electrons transfer. I don't really like that bond. I should have changed it. So can we think of it as bonding, please? So let's just put that there. So it's ionic bonding. We've got to show or represent this electronic transfer. We're going to learn about something called dot and cross diagrams. They're essentially what you did in an atomic structure, where you used crosses to represent electrons. We're just also going to do versions with dots, and we'll explain why we do that when we come to it. Work out the charge on the ions of elements in groups 1, 2, 6, and 7. And then finally be able to draw dot and cross diagrams for ionic compounds that involve elements in groups 1, 2, 6, and 7. So we talked previously about how all bonding was an electrostatic force of attraction, and that it was strong, and it was between oppositely charged particles. And with ionic bonding now, those oppositely charged particles are ions. So when you did atomic structure, you should have done times when an element either gained an electron or electrons, or lost an electron or electrons. And so as a consequence of that, you had now a different number of protons and electrons. So you had an overall charged particle, and that charged particle was called an ion. So in an exam or anything, if they use the word atom, then that must mean that it's neutrally charged overall. So you have the same number of protons and electrons. And if they use the word ion, then you're talking about a different number of protons and electrons. And the way that difference will have come about will be because the the original atom has either lost electrons to become positively charged, a positively charged ion, or it has gained electrons to become a negatively charged ion. Okay, so now we're looking at working out the charge on the ions of elements in groups 1, 2, 6, and 7. So we're working out the charge on these groups here. And remember, one of the things that the group number tells us is the number of electrons in the outer shell. So also, so group number tells us equals number of electrons in the outer shell. Now, if you're to get a full outer shell, you're either going to need to lose electrons or gain electrons. And one of the things to remember is that metals are losers. When it comes to electrons, metals are losers. So what that tells us is if our group 1 elements are to gain a full outer shell, they're going to have to lose 1 electron and they're going to form a +1 ion. Group 2 are going to lose 2 electrons, so it's going to form a +2 ion. Okay. Then when we get to groups 6 and 7, they've got 6 electrons on the outer shell and 7 electrons on the outer shell. A full outer shell is 8 electrons, so group 6 is going to have to gain 2 electrons, which is going to make it -2 charge overall, and group 7 is going to have to gain 1 electron, which is going to make it -1 charge overall. So the point is, if you're looking at an ionic compound, anything in group 1 in an ionic compound has a +1 charge. Anything in group 2 in an ionic compound has a +2 charge. When we get to the non-metals, anything in group 6 has a -2 charge, and anything in group 7 has a -1 charge. And it's a simple pattern. It's something that you can just remember, you can just learn. And again, it's one of those pieces of information that without which the next stage or some of the next stages are going to be very difficult to do. So we've just got a sort of straightforward question here asking us to give 3 examples of an ion for each of the following groups. And these are the 4 that we need to know about, 1, 2, 7, and 6. So why don't you pause the video, write some answers to this on a piece of paper, and then we'll have a look. So in group 1, I could have had lithium, and with a plus charge. I could have had sodium with a plus charge. I could have had potassium with a plus charge. I could have had rubidium with a plus charge, cesium, and I'm not going to bother with francium because hardly any of it exists on the Earth. And really, actually, if you look back at the specification for the atomic structure section, they want you to know about the elements up to and including element number 20, which is calcium. So in a GCSE, you're really only going to get in group 1 any questions that are going to be relevant are going to be lithium, sodium, and potassium, and they all have 1+. Group 2. So when we look at group 2 and we look at the elements that are present in group 2, I could have written beryllium, 2+. That's very rarely comes up actually. Magnesium, that is a common one, so that's 2+. Calcium, 2+. And then really anything beyond that is unlikely to come up. But strontium is one of them, and we'll just do barium as well. So calcium is the last element you're supposed to know or be able to do the atomic structure for according to the specification for the atomic structure section. When we look at group 7, that's the halogens. So we could have F- because they form 1- charge. We could have Cl-, chlorine. We could have bromine, so Br-. We could have iodine, I-. They're very unlikely to have astatine, but if we were to have astatine, it would be At-. So the periodic table, it's called a periodic table because there are repeated patterns. They repeat themselves periodically. And that's what we're observing here. One of the things we're observing here is how the charge is the same for the ions, for group 1 ions, group 2 ions, group 6 ions, group 7 ions. And with group 6, they have to gain 2 electrons, so they're all going to have 2 minus charge. So we're looking at O2 minus for oxygen. We're looking at S2 minus for sulfur. And we're looking at selenium, that would be S2 minus, and we're not really going to bother with anything beyond that. All right, so now we're coming to this idea of dot and cross diagrams. So you've done cross diagrams before in atomic structure when you've drawn the atomic structure for, say, lithium. So if we put, so this is lithium in the first shell, and then the second shell, and you'd look on the periodic table, and lithium has 3 electrons, or an atomic number of 3, so it's 3 protons. It's an atom, so 3 electrons. We put the first 2 on the inner shell, and then it's full, and then we put the third on the second shell. So you've used crosses to represent electrons before. You're also now going to use dots to represent electrons, and we're going to use crosses for one element's atoms, and we're going to use dots for the other elements, and it's just going to make it a lot easier to see where the electrons have transferred. When we form an ion, so when we've either lost or gained electrons, then one of the things that we have to do is we have to put brackets around it, and we also have to put the charge on the top right. So just outside the brackets on the top right. And then I wouldn't worry so much about this. Make sure you put the ions close together, but you know they are going to be attracted to each other. We're going to have opposite charges, so you should put them right next to each other. So let's consider sodium and chlorine, which can react together to form sodium chloride. So we're looking at them as elements to begin with. So we're just filling in the number of electrons in the shells for these particular elements. So sodium has an atomic number of 11, which means as an atom, which is neutrally charged overall, there must be 11 electrons. So I put the first 2 in the first shell because that's the maximum. And then I can put a maximum of 8 in the second. So that takes me to 10 electrons. So I've got 1 left over. So that goes on the outer shell, and sodium is in group 1 and it has 1 electron on the outer shell. Chlorine has an atomic number of 17, so it's going to have 17 electrons. So I'm going to do these as dots just to sort of differentiate them. Of course, all electrons are exactly the same, but we're just making it clear when we see the result of the reaction, it makes it clearer to see what's happened. So that is now 17 electrons. So I've got 17 electrons on my chlorine. Now, when sodium and chlorine react, the whole idea is they both end up with a full outer shell. And we've got to consider how that's achieved. And one of the things that we said was that metals were losers and non-metals gain electrons. And so what's going to happen during the course of the reaction is the outer electron in all of the sodium atoms is going to transfer to the chlorine atoms. Okay, so we're just representing that by showing an arrow. That's just representing the transfer of an electron. So this is now the electronic arrangement or structure once the transfer has happened. Now the sodium atom lost 1 electron, so it's going to have become an ion because it's now going to have an unequal number of protons and electrons, and we show that it's an ion by putting the square brackets around the electronic structural arrangement. We lost 1 electron, we lost a -1 charge, so overall the sodium ion, because it is an ion now, it has got a plus charge. We don't write +1, we just write plus. If you did write +1, it's fine, right? You get the mark, but the convention is just to write the plus. The chlorine gained an electron, so that means it's also an ion. So we draw these square brackets, and it gained 1 electron, so it now has a -1 charge, and we show that with a minus on the outside. So this is our dot and cross diagram showing the ions formed when sodium and chlorine react together. So let's now see another example. So we're going to react together lithium and oxygen. So we draw the electron arrangements for their atoms, and so lithium has an atomic number of 3, so it has 3 electrons, so 1, 2, and then the third one is on the second shell of this, which is its outer shell, and obviously you'll understand why I've drawn 2 in a second. Okay, and then oxygen has an atomic number of 8, So there's the first two, and then I've got another 6 to put on, and I'm going to put them on like that. Okay, so again, metals lose electrons to get a full outer shell, non-metals gain electrons to get a full outer shell, and so what's going to happen is the outer electron from the lithium atoms is going to transfer to the outer shell of the oxygen atoms. Oxygen needs to gain 2 to have a full outer shell. Lithium needs to lose 1. Really, the reason I'm drawing 2 lithium atoms is because I need 2 lithium atoms for every 1 oxygen for this reaction to take place. So these are the electron arrangements once the transfer has taken place. So obviously each lithium atom has lost an electron, so now they're lithium ions. So we show that by drawing the square brackets. And then they each lost 1 electron, so they now have a 1+ charge. And then oxygen gained 2 electrons, so that's obviously now an ion rather than an atom. And it gained 2 electrons, so it's a 2- charge. Now let's consider magnesium reacting with oxygen. So magnesium has an atomic number of 12, so it's going to have 12 electrons. So the first 2 on the inner shell. That's 10 so far. So, and then there are 2 on the outer shell, and it's in group 2, so that makes sense. Oxygen we've already done, has 8 electrons. And it was in group 6, so it has 6 electrons on its outer shell. So magnesium needs to lose 2 electrons. Oxygen needs to gain 2. So every magnesium atom is going to transfer 2 electrons to oxygen atoms. So this is what we get as a result. Each magnesium atom has lost 2 electrons, so it's obviously an ion. And if it's 2 electrons it's lost, it has a 2+ charge. And we'd already done oxygen. It's gained 2 electrons. It's going to have a 2- charge. And this also follows, what we were doing earlier about how group 1 elements form 1+ ions, group 2 elements form 2+ ions, group 6 elements form 2- ions, and group 7 form 1- ions. So now we're at the next bit of the specification where it introduces a little bit more information on ionic compounds. So one of the things you'll notice, hopefully, when you read what's here, it says a giant structure of ions here, which is not how it's appeared to be on the dot and cross diagrams we've just done. We've been showing 1 magnesium ion, 1 oxide ion, but actually what this is saying is there is a giant structure, and you begin to get an idea of that from the pictures you can see there. You can see it's still saying strong electrostatic forces of attraction. That's something, it's relevant to all of the bondings that we're looking at. So what we're actually going to look at first is one of the last things it mentions in this text, and that is working out the empirical formula of an ionic compound. So we're going to understand why the formula of magnesium fluoride is MgF2, why the formula of magnesium oxide is MgO, why the formula of sodium chloride is NaCl, and why the formula of sodium oxide is Na2O. So we're going to understand why those formulae are what they are. So it's introducing a new term for us, empirical formula. And an empirical formula is simply a formula that shows us the simplest ratio of ions. So when we see a formula like NaCl, what that's telling us is that for every 1 sodium ion, there is 1 Cl- ion. And for a formula like MgCl2, what that's telling us is that for every 1 Mg2+ ion, there are 2 Cl- ions. So it's a ratio, right? It's a ratio of ions. So we're going to just look at a system for working out the formula of a compound. So this is very broken down, what we're about to do, or it's a very broken down system. At the bottom I say a quicker method. I'm actually going to do that on the next slide. I should have deleted that here. So we'll start with sodium chloride. The symbol for sodium is Na. The symbol for the chloride or chlorine is Cl. This is where we need to remember our charges. Sodium is a group 1 compound, so it's going to be the value. We're just writing the value. We're not writing whether it's plus or minus. We're just writing the value. So that's 1. And for a chloride ion, it's 1. We're going to swap those numbers, which of course they're exactly stay the same. We're going to simplify them. Again, stay the same. And then the final number that we've got tells us how many of each we should write in our formula. So if it's just 1, you just write the symbol, and I do that for both sodium and chlorine, and that's the formula for sodium chloride. If we look at magnesium oxide, symbol for magnesium is Mg, symbol for oxygen is O. Mg is in group 2, it will form a 2+ ion, so the value of its charge is 2. Oxygen is in group 6, so it will form a 2- ion, so that's got a value of charge of 2. We swap them, of course that means they stay the same, but we can simplify them because we try and find the simplest ratio. So at the moment we've got 2 to 2, so we can simplify that to 1 to 1. So our formula is going to be Mg and then O. If we look at calcium fluoride, calcium symbol is Ca, fluorine is F. Calcium is in group 2, so the value of its charge will be 2. Fluorine is in group 7, so the value of its charge will be 1. Here we do actually notice the swap, so we swap the numbers around. We can't simplify them any further than 1 to 2. So we're going to write calcium, there's only 1, and then we're going to put 2 after the fluorine. Right, so that number, that's that number that we ended up with in the simplification, that's what we put after the element. Lithium oxide, lithium is Li. Oxygen is O. Lithium forms a 1+ charge. Oxygen forms a 2- charge. We swap the numbers. We can't simplify them any further than 2 to 1. And then we're going to write Li. And then we've got 2 in our line above. So Li2, it's a subscript. So subscript means below the line. So it's the smaller number and then O. And there's our formula for lithium oxide. And then finally, cesium bromide. So Cs is cesium, Br is bromine. It's group 1, so it's 1. Group 7, so it's 1. We swap them, but obviously that's the same. We simplify them, they're obviously the same. And then the formula, therefore, of cesium bromide is CsBr. This is essentially the same method. It's just done a little bit quicker. So the thing is to write the charge of the 2 ions. So if we were doing magnesium oxide, the ions are Mg2+ and O2-. Then it says if the size of the charge of the 2 ions is the same, okay, which it is here. So we've got 2 and we've got a 2. Then the formula is simply the 2 symbols together. So the final formula for us is simply MgO. If, however, they're different, so let's pick calcium chloride. Let's say calcium chloride. So calcium has a 2+ charge because it's in group 2, and chloride has a 1- charge because it's in group 7. Then what we do is we take the number before the charge. Okay, so that's 2 in there before the plus there, and there's no number, but we'll still circle just before it, and we do an arrow, and what we're going to do is we're going to put whatever is before that charge after the other element. So when we write this now, we're going to write Ca, and then I've circled before the minus and nothing, so it's just Ca, and then it's going to be Cl, and then the arrow has taken that 2 from before the 2+ to after the Cl, so we end up with that. If I just do another example, so if I do sodium and sulfur, so it will be sodium sulfide. I take the value before the charge and I'm going to move it after the other element. And so if I do this one here, the 2 moves after the sodium, and we don't put any number after the sulfur. So that's just a slightly quicker way. Well, it is a lot quicker actually. It's the same, it is exactly the same principle, but it's just a little less broken down. So here's an opportunity for you to practice that. So I suggest you get a piece of paper, pause the video, and have a go at deducing the formulae of these various ionic compounds. So I've just written the ions along the side for each of those parts of the ionic compound. So if I look at lithium fluoride, well, they're both the same charge actually, all right? So I don't even have to do the circle and the arrows. So they're both the same charge, so it's got to be lithium fluoride. I'm just writing the symbols. Rubidium iodide, look at the bits before the charge, they're the same. So I'm just going to write the symbols together. Strontium bromide, I do have a difference. I've got a 2 and no number. So the 2 goes after the Br, and there won't be any number after the strontium. So it's going to be SrBr2. Look at the cesium oxide. They are different numbers, values on the charges. There isn't anything before the plus on the cesium. There is a 2 of the minus for the oxide. So that 2 is going to go after the cesium, and there won't be any number after the oxide. Barium sulfide, they are the same value charge, so it's just going to be the 2 symbols together. Potassium oxide, the different charges, but there's no value before the positive. There's a 2 before the minus, so there's not going to be anything after the oxygen, but a 2 is going to go after the potassium. Sodium sulfide, there's nothing before the positive. There's a 2 in front of the negative. Draw my arrows. So it's going to be Na2S. And then finally, I've got a 2 in front of the plus for the barium. So that moves behind the fluorine. There isn't anything before the minus in the fluoride ions. So we end up with BaF2. So hopefully that has made sense based on the previous 2 slides. So we're on to our next learning objectives. So we're going to describe the structure of a giant ionic lattice, or begin to describe it. We've already talked many times already about the forces holding it together, but we're obviously going to repeat that. There are some finer details that we haven't yet mentioned. And then we're going to talk or see that the different representations, or different ways we can represent ionic compounds sort of visually, and just briefly mention some of the limitations. Obviously, if one was perfect, we would just simply use one. So they all have their advantages, or they all have their benefits, but they also all have their limitations. And one of the things that we have to appreciate in our GCSE is what those limitations are. So we are going to hear a lot about this word, or a lot of this word lattice. And all lattice means is that we have a regular and repeating arrangement. That's all it means. And to be honest, it's something you've done before. It just hasn't been something that you've named. So all the way back to year 7, when you did the particle model, you will have drawn something like this. And that would have been your particle model for a solid. And if you had asked me, or if you did ask me to add more particles, I wouldn't have any problem. You wouldn't have had any problem either. We've got a regular and repeating pattern, and that's all we mean by lattice. And then the giant ionic bit, the ionic is to say that actually what we've got repeating in a regular arrangement are now ions, and the giant is just to get across the fact that we are talking about a very, very large structure. So many, 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 many more circles, if you like, than we would normally have drawn in the past. So we got 4 representations along the bottom here. So this is the first one on the left there is just, it's called a 2D sort of representation. The one to the right of it is showing that more in a 3D sort of perspective. So we've got a number of layers on top of each other. The next one, which if you're, you may see models of these in classrooms or whatever, but this is called a ball and stick model. And then the one on the right is really the same as the 3D, but it gives a much better impression, and it's still far from perfect because it's still too small, but it gives a better impression of the fact that this is a giant structure, that we have this regular and repeating pattern going on and on and on and on and on and on and on. So those are three representations, because I know there are four images, but two of them are sort of the same. The other representation that we have already done was where we drew the electron arrangement with the square brackets and the positive charge. So that's the dot and cross way of representing our ionic compounds. Okay, so we use the dot and cross method to sort of show us how the electrons have been transferred, how many electrons have been lost, how many electrons were gained. The fact that we have these positive and minus charges. So basically we were representing the ions and appreciating their electron configurations. However, the limitation, it's quite a significant one, is that it doesn't show us how the ions are arranged in space. And it certainly doesn't make clear that we have a giant structure, that we have a lattice structure, that we have a regular and repeating pattern. In fact, it gives the impression that one positively charged ion is attracted to one negatively charged ion. And yet when you look at the lattice structures, every positively charged ion is surrounded by a number of negatively charged ions and will be attracted to all of those. And every negatively charged ion is surrounded by a number of positively charged ions and will be attracted to those. So it's great for showing the facts, for showing the electron configurations and structures of the individual ions, but actually in terms of appreciating the structure and eventually the properties of an ionic compound, it has serious limitations in that respect. So what about the ball and stick model? Well, it's great in the respect that we begin to get a much clearer idea of the fact that this is a giant structure, that there's a regular and repeating pattern, that each positively charged ion is surrounded by negatively charged ions and vice versa. But the using of sticks for bonds is incredibly misleading, because what we've got to understand is that the forces of attraction between ions act in all directions, not just simply north, south, east, west, or up, down, left, right. They act in all directions. It also seems to suggest that there's a lot of space between the ions too, which isn't the case. So the 2D space filling representation is definitely useful. It shows more, shows very helpfully how each ion is surrounded by ions of its opposite charge. We can see the regular repeating pattern nice and clearly. But it does, again, have its limitations. So it shows us the arrangement in one layer, but it doesn't show us how the next layer of ions is arranged. So that is a limitation. It doesn't give us the sense of this giant structure that is actually three-dimensional. So then we come to the 3D space filling, and honestly, this probably is the best representation. It gives us that three-dimensional. It shows us still shows us that each ion is surrounded by ions of the opposite charge, but it only shows the outer layer of the compound. So it's harder to see what's going on sort of behind that first layer. But it is probably the best representation, if I'm honest. So that concludes our introduction to ionic bonding. We're certainly going to come back to it. It'll be in another video when we look at the structure in a little bit more detail, and then we think or consider the properties that result from that combination of the structure, the giant lattice aspect, and the bonding itself, and consider how ionic compounds, how their properties come about from a combination of those two things. By properties, we mean things like melting point, conductivity, electrical conductivity, and so on. So now we're moving to covalent bonding. So we've been so far talking about transferring electrons, and in covalent bonding, which if we remember was non-metals only, we're not going to get transfers of electrons, we're going to get sharing of electrons. So we're going to consider what that means and how we can represent it in a bit more detail. So there's our first objective, describing a covalent bond in terms of electron sharing. So the first thing to say, though, is that covalent bonds are very strong. Okay, so they're very difficult to break, and that's going to be important later on when we consider the properties of substances with covalent bonds. The second thing is to remind ourselves about, well, what is this consequence or result of any bonding? And it was something I stressed right towards the beginning of the video, and that is whether it's ionic or covalent or metallic bonding, the consequence of that is that atoms end up achieving a full outer shell. And in covalent bonding, this is achieved by the sharing of electrons. So we are going to be able to talk about there being a single covalent bond. We're also going to be able to talk about there being double covalent bonds, and we're also going to be able to talk about there being triple covalent bonds. Now, when we say when we refer to a covalent bond, what we are talking about is a shared pair of electrons. So we're going to represent that again with crosses and dots to make it clear. But when the electrons are shared, they are shared in pairs. We'll see that clearly, or more clearly, shortly. Now, before we do that, we just have to consider some of the other objectives because it's going to inform what we do. So there's a recall here. So recall just means remember, be able to write it out. So that some covalent substances consist of small molecules. Some have very large molecules, and others have giant covalent structures. Now, what we're going to focus on first are molecular structures. Now, molecules is a word that gets used, I don't know, as if everybody understands what a molecule is. And actually, there isn't really a very clear and definite description of what a molecule is. Like, what is the definition of a molecule? It's actually very difficult to give a simple definition. However, what we can do is have a very clear system of how we can tell whether something is made of molecules or not. And really, that's all we need to be able to do at GCSE and even at A-level, to be honest. So to help us decide whether something is made of molecules, and if it is made of molecules, we can describe it as being a molecular substance, then we can have a very straightforward, or hopefully it's very straightforward, set of questions which we can answer yes or no to, and those answers will tell us about the structure of whatever it is that we're looking at. So the very, very first question that we ask ourselves is it made of non-metals only? Now, we've already said right at the beginning of this video that we can tell whether something has covalent bonding or not because it must consist of non-metals only. So if our answer to this is no, then it doesn't have covalent bonding, and if it doesn't have covalent bonding, it certainly can't be made of molecules, or it certainly can't be a molecular substance. So if our answer is no, then it's not made of molecules. So, if we said NaCl, well, that's got a metal and a non-metal, so it's not made of non-metals only, so straight away that's not molecular, that's not made of molecules. If we look at a substance like magnesium, Mg, that's not made of non-metals only, so that's not a molecular substance. Now, if we answer yes, that only takes us to the next question. It doesn't mean that we definitely have something that's molecular. Now, our next question is actually a pair of questions, and we only have to answer yes to one of them. So the two questions are, is it made of more than one non-metal? And does it have a subscript in its formula? And if you answer yes to just one of those questions, then it's molecular. So to give you a couple of examples that fit that requirement. H2. So is it made of more than one non-metal? No. Does it have a subscript in its formula? Yes. So it's molecular. Another example might be hydrogen fluoride. Is it made of more than one non-metal? Yes. Therefore, it's molecular. Sure, it doesn't have a subscript, but we've answered the first question with a yes. And then a final example is glucose, so C6H12O6. Is it made of more than one non-metal? Yes. Does it have a subscript in its formula? Yes. So that, well, we only need to say yes once. That is also a molecular substance. If it's a no at this stage, so we have confirmed it's made of non-metals only, so we have confirmed that it's has covalent bonding, but then if we fail to say yes to both of those questions that we then ask, then it's what we call, and we'll learn more about this in another video, it's a giant covalent structure. And so examples of that are carbon and silicon. Now, there is one exception to this, to what I've written here, and that exception, so I'm going to write it here, is silicon dioxide. So that is made of more than one non-metal, and it does have a subscript in its formula. However, it is not a molecular substance. It is actually a giant covalent. So it's the one thing that doesn't fit these rules, I'm afraid. But if you just remember silicon dioxide doesn't follow these rules, then you'll be okay. And we will learn about silicon dioxide separately anyway. So we need to test our understanding of this. So we're now going to have a look at a list of substances, and then you are going to decide whether they are molecular or not. So there is a list of substances, starting with oxygen at the top. So we've got about half of them have their formulae, and then the second half are written as names. You may not know what some of those substances are yet, but by the time you finish your GCSE, you will. So why don't you pause the video, have a look back at the flow diagram we just saw, and then decide whether each of these substances is molecular or not. Okay, oxygen. So it's made of non-metals only, and it has a subscript in its formula, so it is molecular. CO2 is made of non-metals only, it has more than one non-metal, and it has a subscript in its formula, it is molecular. Potassium iodide does not have non-metals only, so straight away that's not molecular. MgCl2 does not have non-metals only, magnesium is a metal, so that is not molecular. C60 is made of non-metals only. It is not made of more than one non-metal, but it does have a subscript in its formula. That is a substance called Buckminster fullerene, and we're going to learn more about that in a separate video. Fe is iron, so straight away that's not non-metals only. Hydrogen bromide, it is non-metals only. It is more than one non-metal, so it is molecular. C10H22O is non-metals only, and it is made of more than one non-metal. It is made of molecules. It is molecular. Aluminium oxide, so straight away aluminium is a metal, so that cannot be molecular. NH3 is ammonia. It is made of non-metals only. It does have more than one non-metal in its formula, and it does have a subscript, so that is molecular. Hydrogen fluoride. So you might not know what the actual formula is, but you know it's got hydrogen and fluorine in it, and those are the only two elements. So it's non-metals only, and it's more than one non-metal. So yes, that's molecular. Methane is something you're going to learn more about. It has the formula CH4. It's the fuel in gas cookers. So that's non-metals only, and more than one non-metal, and it has a subscript in its formula, so that is molecular. Graphite, you will discover, is one of the structures that carbon forms naturally. So it is non-metals only, However, it's represented with the symbol C because it's just carbon. So there's no subscript, and it is not more than one non-metal. So that, I'm afraid, is not molecular. Glucose, we've already seen, C6H12O6. Non-metals only, more than one non-metal, has subscript numbers in its formula, so that's molecular. Phosphorus trichloride, so the tri means 3, so it's PCl3, it's phosphorus and then 3 chlorines. Non-metals only, it's more than one of them, that would be enough, but also if we realise what trichloride means, that would also tell us it has a subscript in its formula, so that is molecular. Sulfur dioxide, more than one non-metal, 2 of them, so there we go. Silicon dioxide. Now here's where we've just got to not fall foul of the trap. Silicon dioxide is the exception to the rule, or the exception to the diagram we drew. So you've just got to remember that as a giant covalent structure. So it's not molecular. Calcium carbonate. The moment we see calcium, that's a metal, so it cannot be molecular. Water, H2O, made of more than one non-metal, it's non-metals only, and it has a subscript, so yes, that's molecular. And then diamond, well, you might not know what diamond's made of, but it's another version of carbon, so we would still represent it with just a C. So it is non-metals only, but it is not more than one non-metal, and it does not have a subscript in its formula, so that is not molecular. So just as we could represent ionic compounds in different ways, I mean visually, it's the same for covalent bonds. So I've drawn two, I've got here 2 dot and cross diagrams. They are obviously the same, really. It's just that sometimes we draw circles, and in fact, actually in your GCSE it will be with circles, but you can also see it without the circles, but they are really showing the same thing. And then we've got something called displayed formula. So that's a very, very common way of representing molecules or drawing molecules. So at A-level chemistry in particular, you would be drawing a lot of molecules in this way. Then we've got 3D space filling. So it's sort of giving you a sense of the volumes, I guess, of each part of the molecule. And then we've got something that's called a ball and stick, like we had with or ionic, and so we have each atom and then a stick to any connected atoms. So let's just remind ourselves, covalent bonds. Okay, so if we remember about covalent bonds, they are shared pairs of electrons. So in these diagrams, that is a covalent bond. Okay, so that's a shared pair of electrons, and the dot and the cross is to show that one of them has come from one of the atoms. The dot, say, has come from the carbon here, and the cross has come from the hydrogen. They're both electrons. There's no difference between them. It's just to show. It just gives us a useful representation of where the electrons have come from. Obviously, that's the same in the second dot and cross diagram. In the displayed formula, every line that you see is representing a covalent bond. So every line that you see in a diagram, that is a dot and a cross, if you like. Okay, it's a shared pair of electrons. 3D space filling, really hard to show exactly where the covalent bond is. It is a little bit easier with the ball and stick, because that's what the stick is supposed to represent. That's where the pair of shared electrons are, or the shared pair of electrons is. So again, just as we had with the ionic compounds, and the fact that we could represent ionic compounds in different ways, and they had their advantages, but they also had their limitations, that is also the case here with covalent substances. So we will have to just consider briefly the limitations with each of the different diagrams that we've got. So dot and cross diagrams feature heavily in your GCSE. You're going to have to draw dot and cross diagrams for various simple molecules, which you'll do shortly. But the limitation here is that we don't have a sense of the relative sizes of the atoms. They're not all the same size. And we also don't have a sense of how they're arranged in space. Now, to be honest, at GCSE, that doesn't really matter, because you never really consider them in terms of three-dimensionally, and you never really consider them in terms of having relative sizes of atoms. At A level, it's quite a different thing, and the 3D shapes is very important. And in fact, the 3D shape is very important to the chemistry of many of these molecules. But at GCSE, it doesn't really matter, but that is the limitation that we have to acknowledge. So that brings us to displayed formulae, which also feature very heavily actually at A level and do feature at GCSE. Certainly when you get to the organic chemistry section, you will have to draw some simple displayed formulae like the one that we've got here for methane. Limitations wise, similarly, they don't show us the 3D structure of the molecule or the 3D arrangement, how the atoms are arranged in space. And they also don't make it clear which atoms the electrons in the covalent bond have come from. Again, it's not a huge problem for GCSE, but we have to acknowledge those limitations. And we come to 3D space filling, and to be honest, actually, you won't, even if you looked online, you won't see this very often. The main reason is it's not terribly useful, and it does. The one benefit it has is it gives us a sense, or can give us a sense of the size of the different atoms involved in, or the different atoms present in a molecule. And in some instances, there are significant differences in sizes, and that can be quite useful to know that, to appreciate that, and actually can be quite important for the chemistry of that particular molecule. But really, the problem is that, well, it doesn't show the bonds themselves. Maybe that's not the worst thing in the world, but it can get incredibly confusing once you start to add a number of atoms. So for large molecules in particular, where there are lots of atoms to include, it would be extremely confusing. So finally, we have the ball and stick model, and in fact, you may have used them, but you've probably seen where people make molecules using coloured balls to represent particular elements, and then they've got these little plastic sticks that join them together. They can be quite useful, and what they certainly give you a sense of is the three-dimensional structure, and that can be very useful. And their limitation isn't the biggest. It's simply that they don't show you where the electrons in the bonds have come from. That's not the worst thing in the world. And in fact, in a sense, they're a bit like a displayed formula. They're actually like a three-dimensional displayed formula. But we have to acknowledge that limitation, basically. So that covers the limitations of the different models that we have for representing simple molecules. Now we have to look at covalent bonding in terms of dot and cross diagrams. And very kindly, I guess, the specification actually lists which molecules you need to know. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 molecules that you need to be able to do dot and cross diagrams for. You obviously don't want to just simply memorize them because that's a lot of information to retain, and also it's always much better to sort of understand what you're doing. So we're now going to look at each of those, also the odd other example, just to get a sort of a firmer understanding of what we're doing when we're trying to do dot and cross diagrams of these molecules, these simple molecules. Now, just as we had with ionic compounds, a sort of a pattern on the periodic table. So group 1 forms +1 ions, or 1+ ions. Group 2 forms 2+. Group 6 forms 2- ions, and group 7 forms 1- ion. Sorry. We have a pattern also in the periodic table when it comes to covalent bonding. Now, covalent bonding only applies to nonmetals. So we're only going to be looking at groups 4, 5, 6, and 7. So there is a quick way of working it out. So we can put those 4 groups. So we're doing group 7, group 6, group 5, group 4. Let's have an example element in each. So let's have chlorine for group 7. Let's have oxygen for group 6. Let's have nitrogen for group 5. And then let's have carbon for group 4. And then to work out how many covalent bonds each needs, we just have 8 minus the group number, right? And that's going to tell us how many shared pairs of electrons each needs to have. So 8 minus 7 equals 1. So chlorine will only ever form one covalent bond. That means we will only ever draw chlorine with one shared pair of electrons. Oxygen will form 2. Nitrogen will form 3. And carbon will form 4. And the only other one to mention, because it sort of sits there on its own, is hydrogen, and hydrogen will only ever form one covalent bond. So this is useful because when we start to do the dot and cross diagrams, we already have something to give us like a strong guidance. Now, in exam papers, they will always give you the atoms with these circles, and those circles are representing the outer shell. And they will do that so that there are overlaps. And if you're a covalent bond, there will have to be overlaps because that's how we're showing which pairs are being shared. And the great thing is these overlaps tell us where we're going to put our shared pairs of electrons. So if we know how many covalent bonds and therefore shared pairs of electrons a particular element must have, then we already know what we need to put into the overlaps. So let's take that sort of like step by step. So we start with hydrogen, right? We already know the formula is H2. We know that hydrogen only ever forms one covalent bond, so there will only be one shared pair of electrons. Whenever we're drawing shared pairs of electrons, they have to go in where the shells overlap. So I put a cross and a dot, right? So that's a covalent bond. That's a shared pair of electrons. Then the next thing you do is you count how many electrons you've put down already, in those overlaps. So I've put one cross and one dot, and then you consider how many electrons those elements are supposed to have in their outer shell normally. And hydrogen does only have one electron in its outer shell, so I will only be drawing one cross and only one dot. And then as like a final check, you would go around the element and just count the electrons around that element to know, because remember that the consequence or result of all bonding has to be a full outer shell. So if I go around the hydrogen on the right and I count, I go 1, 2. So I've got 2 electrons on that now, on that outer shell for hydrogen. And it is in the first period. That is a full outer shell. So that's correct. And obviously the other one is the same, but let's just do it. So 1, 2 electrons go round, and that also has a full outer shell. So everything's good. And we describe if we have just a pair of electrons in an overlap. So we just have one dot and one cross in an overlap. That is called a single bond. Okay. Let's have a look at fluorine. Now, fluorine is in group 7. So to work out how many covalent bonds it should have, it's 8 minus the group number. So 8 minus 7. So it's going to have one covalent bond. So there's going to be one cross and dot together. And they have to go where the shells overlap. So that has to go here. Okay. Now, fluorine is in group 7. So I should be drawing 7 crosses in total and 7 dots in total. Now, I've already dealt with the overlap, so any crosses that I add now must be on the outer shell of, say, the left-hand fluorine. We'll choose that one to have the crosses, but they can't be in the overlap. So I put them outside the overlap, but still on the outside shell. And then obviously the other one is going to have 7 dots in total. I've already drawn 1, so I've got to draw 6 more. Okay. And then I take the left-hand fluorine and I count the electrons on the outer shell. So 1, 2, 3, 4, 5, 6, 7, 8, a full outer shell. Take the one on the right, 1, 2, 3, 4, 5, 6, 7, 8, a full outer shell. So that all looks good. Displayed formula is the atoms, and then for each covalent bond you draw a line. So that is the displayed formula for fluorine. Type of covalent bond, there is only a single line between the two fluorine atoms, so that is a single bond. Let's do chlorine. Chlorine is also in group 7. So the number of covalent bonds is 8 minus 7, so 1. So in the overlap, I am just going to draw a dot and a cross, a single dot and a single cross. Chlorine should have 7 electrons on its outer shell, so I should be drawing 7 crosses in total. I've got to draw 6 more. They can't be in the overlap, so I draw them elsewhere on the outer shell. And the same with the dots. The one on the right should have 7 dots. Okay. Now let's start with the chlorine on the left and count all of the electrons on the outer shell. So 1, 2, 3, 4, 5, 6, 7, 8. So it's a full outer shell, and the one on the right, 1, 2, 3, 4, 5, 6, 7, 8. Also a full outer shell. Displayed formula, chlorine, there is one shared pair of electrons between the two chlorine atoms, so there's one covalent bond. That's the displayed formula, and it's a single bond. Bromine, group 7 again. So 8 minus 7, there's one covalent bond, so 1 cross and dot. Bromine's in group 7, so there should be 7 crosses in total. The other 6 must be on the outer shell, but not in the overlap. Same with the dots. So this is exactly the same as the other 2 that we've just done, because they're all halogens, so they should be the same anyway, right? So I'll just scoot through that. And that's also single. Then we've got hydrogen chloride. So hydrogen, we know, only forms one covalent bond, and chlorine also only forms one covalent bond. So we're going to have 1 cross and dot, and we're going to put them in the overlap there. Hydrogen does only have 1 electron in its outer shell, so it's just 1 cross. Chlorine should have 7, so I've got to draw 6 more dots. Okay. So let's count our electrons on the outer shell. So hydrogen is in period 1, so it's only going to have the first shell. So it should have, to have a full outer shell, it must be 2 electrons. 1, 2. And chlorine should have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So both have a full outer shell. We draw for the displayed formula the symbols, and we connect them with however many covalent bonds there are between each atom. There's just 1 pair of electrons, so 1 covalent bond. So we draw the displayed formula like that. And again, it's a single bond. Okay, so now we're ramping it up a bit. So we've got methane, and that has the formula CH4. And carbon is in group 4, so it will form 8 minus 4, which is 4 covalent bonds. So we're going to have to draw 4 pairs of dots and crosses. Each hydrogen will form 1 covalent bond, so each hydrogen will have just 1 dot and 1 cross. We've got 4 overlaps. I've got to draw 4 pairs of crosses and dots, or dots and crosses, so I'm going to put 1 in each overlap. So let's say the crosses are the carbon electrons. Well, carbon is in group 4, so it should have 4 crosses, and we already have drawn 4 crosses. And we've obviously drawn for the dot the 1 electron that each hydrogen has. So that is complete. But we just do our check with the full outer shell. So we can see each hydrogen has 2 electrons on its outer shell. So they're all full. And then if we look at carbon and we follow it round, it has 8 electrons now on its outer shell. So that is also full. Now when we come to draw the displayed formula, the thing I think to do is to draw the central atom. If there is a central atom, draw the central atom, and this is clearly carbon. And then it is got a covalent bond with the hydrogen to the right. one to the left, one above, and one below. And each, when we look at the covalent bonds between each carbon and each hydrogen, they are all single covalent bonds. So that is still, they are still single covalent bonds. Okay, to ammonia. So ammonia has the formula NH3. So nitrogen is in group 5. 8 minus 5 equals 3, so they will have 3 covalent bonds. So I need to draw 3 pairs of crosses and dots around the nitrogen. They can only go in the overlaps, and I have 3 overlaps. So there's going to be 1 in each. And that's good because hydrogen will form 1 covalent bond. So that's 1 pair for each hydrogen, and that works. Now, nitrogen is in group 5. So let's say the crosses are nitrogen's electrons. I've drawn 3 crosses, but group 5 says I should have 5 electrons, so I should be drawing 5 crosses. So the 2 remaining crosses must be outside the overlaps on the outer shell of nitrogen, so they're going to go, say, there. And then when I look around the nitrogen, there are 8 electrons. It's a full outer shell, and obviously we've dealt with hydrogen many times now. It's got 2 electrons on its outer shell, so that is full. Drawing it. Again, pick the central atom, which is clearly nitrogen, and I've got 1 covalent to the hydrogen to the right, 1 covalent bond to the hydrogen to the left, and 1 covalent bond to the hydrogen below. And each of those, between each hydrogen and nitrogen, there is just a single bond. Water. So oxygen is in group 6, so it will form 8 minus 6 covalent bonds, which is 2. So I've got to draw 2 pairs of crosses and dots. I have 2 overlaps, so I've got to put 1 in one overlap and the other in the other overlap. Let's let the crosses be the oxygen's electrons. So I've drawn 2. It's in group 6 though, so there should be 6 crosses in total, so I've got to draw another 4. So I put those outside the overlaps, and then I check. Look, there's 8 electrons around the oxygen, full outer shell, and we've dealt with hydrogen a number of times before. 2, that's fine. Didn't actually write the formula, did I? But you knew that water was H2O. Displayed formula, take the central atom, which is oxygen, and then it has 1 shared pair with the 1 hydrogen and 1 shared pair with the other hydrogen, and between each hydrogen and the oxygen there are just single bonds, just 1 shared pair. Alright, so now we have some more. We have O2, so oxygen on its own. Okay, so oxygen is in group 6. 8 minus 6 is 2, so there are 2 covalent bonds, 2 pairs of crosses and dots. There is only 1 overlap, so both of them must go in that overlap. And then let crosses be the electrons for the left-hand oxygen. So I've drawn 2 crosses, but oxygen is in group 6, so I should have 6 crosses in total. So I've got to add another 4, and they can't be in the overlap. And obviously the same with the dots to the one on the right. So let's draw the symbol for the left-hand oxygen. Now there are 2 pairs of electrons being shared, so I'm going to draw 2 lines. That's how I'm representing the fact that there are 2 shared pairs of electrons. That means 2 covalent bonds. That is called a double bond. Okay. Carbon dioxide, CO2. Oxygen, let's stay with the oxygen. So oxygen is in group 6, so 8 minus 6 equals 2, so 2 covalent bonds. So each oxygen must have a pair of crosses and dots. Each oxygen only has 1 overlap, so I'm going to put those pairs in each overlap. Let's the carbon be the crosses. Carbon is in group 4, so there should be 4 crosses, and I have already drawn 4 crosses, so that's fine. Oxygen, that's the dots. It's in group 6. I've only drawn 2 dots for each oxygen, so I've got to draw another 4, but they can't be in the overlap. And then if I go around each atom, so around the oxygen on the left, 1, 2, 3, 4, 5, 6, 7, 8 electrons, that's full. Around the carbon, 1, 2, 3, 4, 5, 6, 7, 8, so that's full. And around the oxygen on the right, 1, 2, 3, 4, 5, 6, 7, 8. So they've all got full outer shells now. Displayed formulae. Let's draw the central atom first, carbon. So there are 2 pairs of electrons being shared with the oxygen on the left, so I draw 2 lines, and 2 pairs of electrons being shared with the oxygen on the right, so I draw 2 lines. Between oxygen and carbon there are 2 covalent bonds, so that is a double bond. So finally nitrogen, N2. Okay, so nitrogen is in group 5. So the number of covalent bonds nitrogen forms is 3. So I've got to draw 3 crosses and dots. There is only 1 overlap, so all 3 of them must go in that overlap. So cross dot, cross dot, cross dot. Nitrogen should have, so let's do the crosses for the one on the left. I've drawn 3 crosses, but nitrogen is in group 5, so there should be 5 crosses. And then for the one on the right should be 5 dots. If I check around the outer shell, 1, 2, 3, 4, 5, 6, 7, 8, that's full. 1, 2, 3, 4, 5, 6, 7, 8, that is also full. And then our displayed formula, nitrogen, and then I've got 3 shared pairs of electrons, so 3 lines, and then the other nitrogen atom, and that is called a triple bond. Now, it is possible to have some very large molecules, and you will learn a lot more about these, the polymers, in year 11, or whenever you do organic chemistry anyway. They can be really large. You are familiar with polymers because all the plastics that you are aware of or use are all examples of polymers, so polythene and polystyrene. They are really large molecules, and the polymer stands for many parts, so they've been made up of the same part repeatedly. So if you look at these long chains that I've got here, if I just cut them in different places, you can see that there's like a repetition. So you can see how it's being repeated. And we can do a sort of shorthand version of what we've got represented here. And that's really all we have to do at this point. We have to recognize that you can have very large molecules. And we have to sort of, if they're in the case of polymers, we have to be able to show how we would represent them. So you can see what that repeated unit is. The repeated unit is 2 carbons connected, and then we've got a hydrogen and a hydrogen going up above, and then we've got a CH3 and a hydrogen going below. What we have to show is that continues, so we have to draw the bonds to the left and right, but then we use square brackets to say this is a unit. Okay, it's very important to know that the bonds go through the square brackets. And then to say that this unit is repeated many, many times, we then use the symbol N, and we put that down in the bottom right-hand corner. And in maths, what N always means in maths is it means a very large number. It doesn't say what the number is, but it's just telling you it's a very large number. So what we're showing here is that we have this sort of unit, as it were, repeated many, many, many times, a very large number of times. So that's all we really need to know as far as this part of the specification goes. We need to be aware that there can be some very large molecules, and that polymers, which you will do more on when you do the organic chemistry topic, they are examples of very, very large molecules. And then we just simply have to appreciate how we could represent them, because the polymers tend to be, well, they will tend to be repeated units. So in the example we've got here, this is being repeated again and again and again. And to show it's very large, we're saying it's being repeated n times, and n means a very large number. When we did the flow diagram earlier, and our first question was, is it made of non-metals only? And we'd said yes. But then on our next questions, if we'd said no to both, more than one non-metal, and does it have a subscript, then we said it had a giant covalent structure. Three that we are going to do more on are graphite. Three of these giant structures are graphite, and that is graphite on the left there. Another is diamond. Okay, so that's diamond in the middle. And then the third, well, this was the one that we said was our anomaly based on our flow diagram, was silicon dioxide, and that's silicon dioxide there. So these are called giant covalent structures. Even these images don't give a very clear picture. These on the graphite on the left, these sheets here that you've got, they would be carrying on and on and on and on and on, on and on and on, on and on and on. So they would be much bigger than what we're showing here. Similarly, with the diamond structure that we've got here, this would be going on in all directions. We would call these lattice structures, by the way, because you can see there's a regular and repeating pattern. There's a regular and repeating pattern. And then this image for silicon dioxide, I absolutely hate it, but this is often how you'll see it in textbooks. This, believe it or not, the structure here is the same as the structure in here. It's just that we're taking a much smaller sort of part of it. So just like with the diamond, where it just goes, it would go on and 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 on, which is why it's referred to as being giant. This structure here would be going on and on and on and on and on and on, right? They're just enormous, enormous. So now we're at the third and final type of bonding, metallic bonding. This is going to be quite short, actually. What we're going to be more interested in is the properties of metals. But to understand those properties, we've got to understand how the bonding works. So here's our first learning objective, and hey, there's that word again, lattice. All right, so there's going to be a regular repeating pattern. Now we said that we've said that all bonding is a strong electrostatic attraction between oppositely charged particles, and in the example of ionic bonding, it was between oppositely charged ions. In metals, it's going to be between positively charged ions and negatively charged electrons. So we've still got our plus and minus charges. So why does that happen, or how does that come about, rather? So remember, we've said that all bonding comes about because, or the result of all bonding, sorry, is the achievement of full outer shells. So if we think about sodium as a metal, so we can think of lots of sodium atoms in a regular repeating pattern because it is a lattice. If you look at what's drawn here, there is not, they don't have full outer shells, and yet we've said that when something is metals only, for example sodium, there is metallic bonding, and we've also said that any bonding results in there being full outer shells. So what we've got in front of us at the moment, the way we've drawn our electronic structure and shown how shown them in a sort of a regular and repeating pattern, is not accurate. We have still got to achieve full outer shells. What's going to happen is the outer electron is going to move off the outer shell. What we do is we say it becomes delocalized. Now, localized means it's, stays around a particular area or region. You can think of, when you're talking about your local shops or whatever. Delocalized means it's no longer restricted to that place or region. So these outermost electrons, so in our sodium, they have one electron on the outer shell. They are going to become delocalized. So outer electron, but it's electrons because there's lots of these sodium atoms, but the outer electron becomes or is actually delocalized. This is going to explain, when we come to it, a lot of the properties of metals. So what we have here is a much more accurate representation, not perfect, but a more accurate representation of how things really are in metals. So what we think of as being the outer electron of sodium is now no longer restricted to the shell it was in. It's now delocalized. And if it's delocalized, what that really means is that it is free to move. And so these electrons are now free to move all the way through the structure. So we have these metal ions sort of in their fixed positions. So think about your particle model in year 7. We've got a regular repeating pattern. They're in their fixed positions. They might be vibrating around that fixed point. But the electrons themselves are able to move around anywhere and throughout the structure. And this is going to explain many of the key properties of metals. So this is how that is represented in the specification. So it has these two types of diagrams, or two diagrams. They are supposed to sort of be showing the same thing. The one on the left is like our first diagram. So the idea that we have this electron on our outer shell, and then the right hand side is supposed to say, well, actually what happens is that electron on each outer shell becomes delocalized, and so now occupies a region of space in between all of the resulting positive metal ions, which are there because they've lost an electron or electrons, depending on which, how many they had on their outer shell. And so they just they call this sometimes, they sometimes call this a sea of delocalized electrons. So it's not really a sea, but it's quite a useful metaphor, because I guess what it means is, it means these ions are constantly surrounded by negative charge. So this delocalized electrons, what we're saying here is that is negative charge. So the metallic bonding is the attraction between the positive ions, represented by those circles with a plus, and the negative electrons, represented by that sort of grey block, I guess. So that brings us to how we describe metallic bonding, and we do that basically, again, it's a strong electrostatic attraction. So we're saying this also what it's between, only this time it's between metal ions, which are also known as cations. So that's something we'll talk about more of in a future video, but the metal ions and the delocalized electrons, which are negative. And just to reiterate, we have a giant lattice structure. So just from that picture, you can see you've got the nice neat rows and columns of the positively charged ions. That's our lattice structure. If we had to extend that drawing, we could very easily do it. We would know what we would need to do. Those little minus charges in yellow, they are mobile, they are free to move, and that's going to be important when we explain why metals can conduct electricity and conduct heat. But there we have our description of metallic bonding. Okay, so we're going to summarize a lot of what we've just done. So right at the beginning of the video, we stated that there were 3 types of chemical bonding. There is ionic, there's covalent, and there's metallic. And we also began with how we could tell which of those bondings a substance had. So that's how we recognize what bonding a substance has. We also said that all bonding leads to the elements involved having or achieving full outer shells. This can be done either by losing electrons, gaining electrons, or sharing electrons. So we're going to remind ourselves about how that full outer shell is achieved in the case of ionic, covalent, and metallic. Were there any simple rules that we learnt to help us in our understanding of that, whether it was to do with dot and cross diagrams or whatever? And then finally, how do we describe the bonding? How do we describe ionic bonding? How do we describe covalent bonding? How do we describe metallic bonding? So ionic bonding, we can recognise whether a substance has it or not if we have a metal and non-metal in our, well, it will be a compound, right? How do those elements, how does those metals and non-metals achieve a full outer shell? Well, electrons are lost or they're gained. So there's a transfer of electrons. Any simple rules, right? So one of the things that we learned was that metals always lose electrons, and the number that they lose corresponds to their group number. So group 1 will lose 1 electron, group 2 will lose 2 electrons. And then non-metals gain electrons, and they're going to gain 8 minus their group number. So group 7 would gain 8 minus 7, they would gain 1 electron, and group 6 would gain 8 minus 6, which is 2 electrons. And then what is the actual, how do we describe that ionic bonding? We describe it as a strong electrostatic attraction in all directions. Okay, so we'll come back to this in another video, but in all directions. So like gravity exists in all directions. It's not just straight up or straight across, or, you know, if you picture the earth or something. So in all directions between oppositely charged ions, so plus ions and minus ions, in a giant lattice structure. Believe it or not, that whole sentence is potentially 3 marks in an exam. Covalent bonding, we have to have non-metals only. So it could be a single non-metal, but anyway, non-metals only. Full outer shell is achieved by sharing electrons. Each non-metal forms 8 minus their group number covalent bonds. So carbon, for example, is in group 4, so it forms 8 minus 4 equals 4 covalent bonds. These covalent bonds are very strong, and when we talk about a covalent bond, we're talking about a shared pair of electrons. Finally, metallic consists of metals only. Full outer shell is achieved. Remember, we said even in the ionic bit, metals lose electrons, so that's what happens here. So each metal atom loses its outer electron or electrons, and as such they become delocalized. So they're lost, but they're not transferred, so they're still in like the metallic structure. So metals lose electrons corresponding to their group number, just as we had before. And again, there's a strong electrostatic attraction, only this time it's between positively charged metal ions, which are going to also have the name cations, and the delocalized electrons. That's the electrons that were lost from the outer shell. And again, we have a giant lattice structure. And that is the first part of the structure and bonding topic of the Combined Science GCSE. It's quite a lot to take in. I would probably suggest looking over bits of it a few times, but if you have any queries, just let me know.